and this is the algorithm for DFS, BFS, and DFIDN, DFIDC, DFIDC, and DFIDN. So for DFID, let me show you the example. Here we have then we have one state space graph, and we have the movegen function for the state space graph. Now, what are the movegen functions? S can go to A and B. Yes, this is correct. Then A will go to S and C. Correct. B will go to S and D. B will go to S and D. Correct. C will go to E, D, A. C can go to E, D, and A. D will go to B, C, G. To B, C, and G. E will go to C, G. And G will go to D, and A. Now the solution is based on DFIDN algorithm. Adds only new neighbors to open list. Neighbors not present in open or neighbors which are not present in open or closed list. So DFID n search tree for depth bound 0, 1, 2 up to n are shown below, where closed nodes are blue field and open nodes are white field. To reduce the clutter, only the nodes from node pair is displayed in the search tree, but the solution maintains node pair. So what they are saying that depth bound, when the depth is 0, the search node S will be only present. Then depth bound is 2, then we will go up to 1 level. Depth bound is 3, then we will go to second level. 3 and depth bound is 3, then 4, then we will go to 4 level. 5 will go to 5th level. So in depth bound 0, they will search for n, and null means here the parent of S is 0. So there is no parent of S. That's why we will put null in that. Now for node S, close is S null and open is empty, because we are considering only depth bound 0. We are not going further from 0 level. Then if we go to 1 level below, then we will get A and B in the open list. Open list we will get A and B. Parent of them will be S. So they are in the level 1. And if we go to A, we will not get anything, because open will be 0 for B and A. Why? Because we are not considering to go further down. And for depth bound 2, we will go from A and B. So from A, we already know A has C and B has D as neighbor. So for A, we'll go to C, because in the open list C will be present. Then we'll go to C, and for B we'll go to D. But after that we will stop. For depth bound 3, we'll go up to B, C, E, D. Then for depth bound 4, we likewise will go to the open of C is E, D, and B. Then we will go to E. Open of E is Z, D, and B. Then we will go to Z. This is the goal state. We got the path. SAC easy. How you got the path? SAC easy. This is the path. This is DFID N, which is we call this N bound or level. So DFIDC is like it's a different thing, where solution is based on this DFIDC algorithm. These adds new neighbors to open list and also adds neighbors that are closed but not in open list. So in DFIDN, those nodes which are present in closed and open will not be added. But in DFIDC, we will add the node which are present in closed list, but the nodes which are present in open list we will not add further. So if we do that, then what we will get? For S in level 0, we will get only S. Then for level 1, we will get S and S for S, A and B. And for level 2, we will get S, A and B. Then for A, we will get S and C. Why? Because S are in closed list. So we can add here because it is DFIDC. And likewise for B, we can add S. So if we go like this, then for, let's see, for depth bound 3, let's see. For depth bound S, we will get null value. So there is no closed list because parents of S is null. Then we will in the open list we will get one pair which is A and B, and two pair according to the graph AS and BS in the level 1. S is the parent of A and S is the parent of B. Then we will go to A. A has open node as C, but according to DFIDC, we also add DFID which are present in the closed list. That's why they said DFIDC. So we will get new node will be S and C. So for S, we have SA2 and CA2. Here we have shown that the parent of S is A and parent of C is A. Then we will go to S, and again we will get A and B, and again we will go to A, then again go to C, because for A the open nodes are C and B. Then we will go to C, then open nodes of C is E, D, A and B. Then we will go to E, where E has open node D, A, B. Then we will go to D. D has open node of A and B. Then we will go to A. Open nodes are B and S. Then we will go to B. Then B has open node S and D. Then we will go to S again. S has open node A, B, D. Then we'll go to A. Likewise, we will go up to Z. So there are some questions. For a finite state space with one connected component, when does DFS terminates? Well, when goal test evaluates to be true, then DFS will terminate. And when the open list become empty, that is also when DFS will terminate. And for an infinite state space with one connected component, when does DFS terminate? This is a simple function, and for infinite state space, DFS will terminate when goal test evaluates to be true. Again, and for a finite state space with one connected component, under what condition does DFIDN terminate? So when the path is returned by DBDFSN, and when two consecutive calls to DBDFSN returns the same count. And in DFIDN, what does the count returned by DFSN refer to? So number of nodes inspection in the current iteration. Because in DFIDN, we are countering with the n value, and we are using this n value to see what kind of inspection, where we are in the current iteration, and we're inspecting the number of node inspection in the current iteration. And given a highly branching deep search space, where should the goal node appear so that DFS inspect much fewer nodes than BFS? So DFS, if in highly branching deep search space, if goal node appears on the left side, then DFS will inspect much fewer nodes than BFS. और आगे so we are going to discuss about uh, some question where several algorithms will run on the same state space and with the same start and goal nodes. Now for each of these question 1 to 4, 1 2 3 4, so you need to identify this screenshot that would be depicted in the search algorithm and integrated question. What for depth first search, what will be the solution? So screenshot 2 will depict depth first search and screenshot 3 will depict uh, depth first search. And then screenshot 1 will depict breadth first search because breadth first search will search uh, in the, likewise in terms of a circle, but in but for depth first search will search entire state space, and this can be best first search because best first search will try to directly goal oriented, so it will directly try to go to goal, and this will be called as hill climbing because uh, however it also goal oriented, it is trying to find a goal but it will not find the optimal solution and it is just stuck in the local minima. And next, which of these following are heuristics based search algorithms? So best first search is heuristic search, hill climbing and taboo search also heuristic search. Next question, heuristic function will estimate the distance to the goal always. Then next is heuristic search is goal directed. Then some terms commonly used to search algorithms are heuristics, exploration, greedy, state, moveGen function. All of this is used. Manhattan distance is absolute x minus x2 plus absolute y minus y2 for points PQ. And shortest distance from PQ measured along parallel to grid axis. So this will be parallel to grid axis. And for Euclidean distance, this is square root of x1 minus x2 whole square plus y1 minus y2 whole square for point P and Q, and shortest distance from P and P to Q. For a pair of points on a uniform 2D planar grid, Manhattan distance is greater than or equal to Euclidean distance. Let's remember that. And distance here, distance D is a Manhattan distance. Distance C is Euclidean distance, and distance B is the Manhattan distance. And for maximization problem, goal h of goal, heuristics of goal will be greater than or equal to h of node. So we are trying to find the maximum value for this heuristics function. And for minimization problem, we are trying to find the minimum value for the goal function. Then why? Maybe Baby, bu ekmek konuşuyor. Sen 수행된 방어자가 또 것이 모두 수행된 방어에 수행된 모두 방어에 baby, no, not much music. That is that's called the conversion. Please spell that's called the baby. Please spell that's called the conversion. So today we are going to discuss about these heuristic functions and some workout example of dependent on the heuristic function. So this question have A, B, C, D, E as intermediate steps and goal G is the final steps. We are here needed to perform an operation which we can define using heuristic function. We are given 4 heuristic function, and by using those we can go from intermediate steps to goal states. Now yeah. So the heuristic functions were number of misplaced tiles. So if we see what will be the number of misplaced tiles, then we can easily see that for A it is 6, misplaced tiles will be 6, because here 5 4 is misplaced from goal, and 3 is in the correct place, 2 is misplaced, then 1 is misplaced, 8 is misplaced, 7 is in correct position, and 6 is misplaced. So 1 2 3 4 5 6. So sixth number of misplaced tiles is 6 for A. Then for B it will be again 6, C it will be 6, and D it will be 7, and E it will be 6. You can see. And for H2, the heuristic function H2 is like sum of Manhattan distance of the misplaced tiles. So what is the sum of Manhattan distance of the misplaced tiles? So for misplaced tiles, we already get there are 6 misplaced tiles for A. For each misplaced tiles, we need to calculate the sum of Manhattan distance. So how to do this? So for 5 it is 4. I mean the distance where it should be in correct position, 5 should be here. So from 5 in A position to 5 in goal Z position, so there will be 4 value of distance, or 4 meter, centimeter, whatever it can tell in Manhattan distance unit. So 5 should be in here. So 1 2 3 4, and it should be the least distance. That is also need to be correct. So if we sum it up, for again 5 4, then 3 is in correct position, 2 1 8 7 is in correct position, so plus 6, and we will get answer 16. So likewise we can do that. The third heuristic function is number of correctly placed. So for A we can see directly number of correctly placed will be 3 and 7, so it should be 2, and 4 is nothing but h3 minus h1. You can do that. And so which of the heuristic function define maximization problem? Of course h3 and h4, because h3 is number of correctly placed tiles. So it's a maximization. So if correctly placed tiles is maximized, then we are more close to the goal state. And h4 is also maximization problem. Why? Because it is saying h3 minus h1. h1 is misplaced, but h3 is number of correctly placed. So if h1 becomes 0 and h3 becomes maximum value, that is great for h4. This is also will tell us that the number of correctly placed tiles has been considerably increased, and it is mostly close to the goal state, which is good, and this is definitely a maximization problem. Let's compute the h1 values for the state listed above. So we can see that for h1 values, the goal number of misplaced tiles for goal state it will be 0, or it is 6, B it will be 6. Likewise, we can see here, so goal state it will be 0, 6, 6, 6, 7, 6. Next, we can compute the h2 value. It will be, for goal state it will be 0, 16, 15, 15, 18, 15. So you can see that 16, 15, 15, 18, 15. For goal state it will be 0. Next, we can compute the h4 value like this, and then it will come out to be 8 minus 4 minus 4 minus 4 minus 6 minus 4. And according to H2, B is better than A. Why? Because here you can see B's H2 value is 15, but A's H2 value is 16. So B is of course better than A. A is better than D. Why? Because D's H2 value is 18, but A's H2 value is 16. So A is better than D. So if the base neighbor of A better than A, yes, because base neighbor of A is B, and which is 15, but A is 16, so it is better than A. So we'll go to next set of questions of heuristic function. So this is example from lecture is repeated as some H2 values from implementation of this course has been H2 function used in the current edition is different equation. Every block has a level number. A block resting on the table is at level 1. A block resting on the table, resting on level 1 is at level 2, and so on. Now, level numbers are like floor numbers in a skyscraper. So, if we take 4 heuristic functions, H1, H2, H3, and H4, if H1 is like add a 1 if a block is on the correct block, otherwise subtract 1. Then H2 will be for block at level n, add n if block rests on a correct structure below it, otherwise subtract them. H3 is number of misplaced block not in final position. H4 is the number of correctly placed block. So if you see those, then what we will get is you can see here that for goal node, H1 value will be 6. Why? Add 1 if a block is in a correct block. For goal node, this is in correct block because this is a goal state. So 1, next for C1, for B1, for E1, for A1. So 1, 2, 3, 4, 5, and F1. So it will be 6. For S, we will get this is in correct position 1, this is correct position 1, this is correct position 1. A is not in correct position. Next, F is in correct position. So we will minus 1, and here we will also minus 1. So plus 4 minus 2, this will be 2. Like this. So what we will get is H1 value will be 6, 2, 2, 2, 2, 2, 2, 2, and then at the last it will be 4. With 2, 2, 2, 2, 2, 2, 4. Next, H2 value for a block level and if block rests on the correct structure, otherwise subtract. And so what it will do, for example, this is in correct position, we will add 1. This is in correct position, so add 2. This is in correct position, add 3. This is not correct position, so we'll subtract 4. This is in correct position, add 1. This is not in correct position, minus 2. So 3 plus 2, 5, plus 1, 6, plus 1, 7, minus 4, 3, minus 2, 1. So value is 1. So here H2 will be 1, 4, 2 minus 2, 2, 4, 10. And for goal node it is 16. As you can see, goal node 1 plus 2 plus 3 plus 4 plus 5 plus 1. So it will be total 16. So we can calculate this heuristic value. Next, use of this heuristic function define maximization problem. Of course, H1, H2, and H4 will be the maximization problem. Why? Because for H1, if it is increased, and as you can see in the case of goal state, it's plus 6. So more is the value, it is much closer to, it is closer to the goal state, which is good, which is we want, so it is a maximization problem. And for H2, it is also correct. More is the value of the any state, intermediate state, then it is more close to the goal state, which is the maximization problem. And for H4 is also correct because the number of correctly placed law. It is also a maximization problem. H4 is also maximization. So we can answer this question: what is the level number of block A, C, D in goal state? We already know the level number is just 5 to 1 1. For A it is 5, C it is 2, D 1, F 1. Next, if they ask about what is the heuristic value 1 from goal state to X state, we can write it as, or we can compute the H3, we already computed it, we can write it as, and we can write it as for X4, and H2 value of the state is like this. How you get 1? So -3 -4. Yeah. Next question, next set of question. So now, in this question, there are 7 cities and corresponding distance metrics are shown below. We need to compute the TSP tools and table assessment problem, basically TSP means, and the tool cost. Is this given TSP symmetric TSP? Yes, because you can see here, from A to A, B to B, this all are symmetric. So in a tour of n city, this will be correct. Every node has exactly 2 edges connected to it, and then there are exactly n node edges in the tour. Now, well, this is also correct for n greater than 4. When graph has n nodes and n edges, every node has exactly 2 edges connected to it. Then graph may or may not depict a tour in the n cities. Why? Well, because you can see in this example here, this entire graph is not one cycle. So however, every node is connected exactly to 2 nodes, or every node has exactly 2 edges connected to it. So it does not have a single edge of length m, and it's not a valid TSP. It should be on one cycle connecting everything. Next, well, the question is using B as a starting city, construct a tour using nearest neighbor heuristics. Use the distance matrix to compute the tour. So, using nearest neighbor, we already know that from B we can go to F, because from B to F is the smallest one of all of this 41. All of this is the smallest bit one. Then from F we will go to D, because F to D is the smallest. After that, we first go to B to F, then F to D, then I think D2 we should go to E, right? Yes, D2 we should go to E, because from D, E is the smallest. And from E, the smallest one is, I think Z, yes, Z. And from Z, the smallest one will be E, I think E is already done, right? C, it will be C. And then from C, the smallest one will be A. That's it. Tour fee. So, what is the cost of the tour generated by another heuristics? So, we can calculate the cost just by using the calculation, simple calculation. Yeah, this will be the B2D, lowest is 36. We can go there. And what is the cost? We can, if we add all of this, then we will get the answer as 269. Why? 6 to 8. Yes, 41. Then we will add 41. After all of this, we will add 41. So 1 plus 2, 3, 9, and this is 10, so 19. 5 plus 7, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. 269 is the correct answer. Yes, that is. Let's consider two using greedy heuristics. So from greedy heuristics, we will starting from A, we will go to D, E, because um, greedy heuristics is like the first city which we will see as less that we will take from A to D. But A will if A will look further, then it will say that, well, from A I can go to, yes, from A it will go to D, then from D it will go to like E or something. Yes, it will go like this. Next, cost will be generated by this. If we add, so we will get 290. Next, we can perform two city actions. Well, let me show you how to do city actions. So, two city actions is like in the place of, it's like if there is a city like if there is a city like ADEZFAC, ADEZFAC, and if we B and if we exchange the B and E, then what we will get? E become B, and B become E. So it will become ADBZFEC. If we add all of this, then we will finally calculate the what will be the cost. Next, two edge exchange. So edge exchange is slightly different. If we need to change BC and DE interchange these two edge, then if it is the original cycle, original graph, then what will happen is this BC, what was already there, BC and DE, it will get cut off. So from ADE, so D will go to B, D will go to B, and E will go to C. It will be cut like this. So what it will become, A, then in the place of D it will become B,